We have a capacitor, an inductor, and a resistor connected in series with an AC source of voltage amplitude 36 volts and angular frequency 250 radians per second. The capacitance, the inductance, and the resistance are all given. The first question is, what is the voltage across each circuit element at t equals 23 milliseconds? The resistor is in phase with circuit current, and its voltage can be expressed as voltage amplitude for the resistor, that's capital V sub R, times cosine omega t, and the voltage amplitude is equal to I times R, where I is the current amplitude and R is the resistance of the resistor. So this is basically Ohm's law. The inductor, on the other hand, is leading the current by 90 degrees. So in the argument for cosine, we put plus pi over 2, so that's cosine omega t plus pi over 2, and we multiply that by the voltage amplitude for the inductor, which is equal to the current amplitude times inductive reactance for the inductor. The capacitor, on the other hand, is lagging behind the circuit current. So in the argument for cosine, we have minus pi over 2, omega t minus pi over 2, and we multiply that by the voltage amplitude for the capacitor, which is equal to the current amplitude times the capacitive reactance x sub c. So we're going to have to calculate the current amplitude, the inductive reactance, and the capacitive reactance. R is given, the resistance is given, and omega is also given. So these two are given, but I, x sub L, and x sub C, those we have to calculate. And finally, the source voltage is expressed as the voltage amplitude of the source, which is also given 36 volts, times cosine omega t plus phi. Phi is the phase angle of the circuit. If the phase angle is positive, that means the voltage, source voltage, is leading the current. If the phase angle is negative, the source voltage is lagging behind the current. And the phase angle is also something we have to calculate. So let's go ahead and calculate the current amplitude I, the inductive reactance x sub L, capacitive reactance x sub C, and the phase angle phi. The formula for inductive reactance is L times omega, the inductance times the angular frequency. We just plug in the numbers and calculate. Because this is an intermediate calculation, I'm keeping three significant figures. X sub L, the inductive reactance, is equal to 213 ohms. Similarly, we calculate the capacitive reactance. X sub C is equal to 1 over C times omega. C is the capacitance. Omega is the angular frequency. Keeping three significant figures, we get 556 ohms. Note that both the inductive reactance and the capacitive reactance have the units of ohms, which is the same as the units for resistance. Now that we have determined the inductive and capacitive reactances, we can go ahead and calculate the current amplitude in the circuit. The current amplitude is equal to the voltage amplitude divided by impedance capital Z. To calculate the impedance, we combine R, x sub L, and x sub C using this Pythagorean formula. Now, where does this formula come from? It's easier to understand with a phasor diagram. But if you think about it, the voltage of the inductor and voltage of the capacitor are out of phase by 180 degrees. So they're anti-parallel to one another in a phasor diagram. That's why we subtract x sub L from x sub C. You can do it the other way around as well. We're squaring it anyway. But the idea is that the voltages are directly related to reactances. So it's, equivalent to calculate the difference of the voltages. And then to combine R, we use this Pythagorean format. Why? Because the voltage across the resistor is at 90 degrees from both the inductor's voltage and the capacitor's voltage. One is lagging the resistor by 90 degrees, the other is leading the resistance by 90 degrees, hence the use of the Pythagorean format. So Z is equal to square root of R squared plus XL minus XC squared. Substituting the numerical values and keeping three significant figures, we get current amplitude equal to 0.0895 amps, in other words 89.5 milliamps. Now we go back to the time-dependent voltage formula for the resistor and we evaluate it at t equals 23 milliseconds. We get voltage for the resistor equal to 16 volts at t equals 23 milliseconds. Now we calculate the voltage across the inductor at t equals 23 milliseconds. Remember, the voltage amplitude for the inductor is I times x sub L, and the argument of cosine is omega t plus pi over 2 because the inductor is leading the current by 90 degrees. Next, we calculate the voltage across the capacitor using the formula. Keeping two significant figures, we get negative 25 volts for the voltage across the capacitor at t equals 23 milliseconds. Finally, let's calculate the source voltage at the same moment. For that, we need to calculate the phase angle first. The phase angle phi is the inverse tan of XL minus XC divided by R. From that, we get negative 1.02 radians for the phase angle phi. And then we combine everything. We get 0.63 volts for the source voltage at t equals 23 milliseconds. When I add the voltages of the resistor, the inductor, and the capacitor, I get 0.7 volts. By Kirchhoff's loop rule, these actually should add up to the source voltage. In my case, there's a slight difference. I think it's because of my rounding of the values previously. Now let's calculate the voltage amplitudes for each circuit device. Even though we use these values in our calculations of the instantaneous voltages, we never calculated the voltage amplitude separately. Do we expect the sum of these values to be equal to the source voltage amplitude? Absolutely not. Why? Because the resistor, the inductor, and the capacitor do not reach the maximum value of their voltages at the same time. There's a phase difference between them. Based on Kirchhoff's loop rule, at any given moment, we expect the sum of the voltages of these three devices to be equal to the source voltage. But that means the instantaneous voltages should add up to the source voltage value and not the amplitudes.